Okay, so now we're in an escalator. Yay! Because it escalated quickly. In a shopping center. It's designed to move 50 people, okay, 75 kilograms each, at a constant speed of 1.05 meters per second at a 45-degree slope. Woo. Determine the minimum power input needed to drive this escalator. Okay, minimum power input. What would your answer be if the escalator velocity were to be doubled? Okay, this isn't too bad. So this is one of those equations for conservation of energy. We're going to have to write out our different types of energy and figure out how to solve this problem. So when I think of what kind of energy, the answer is actually potential. Like, what about kinetic? It gave us a velocity. It did give us a velocity, but it's at a constant speed, and so we have no change in velocity. So my change in potential energy is equal to mass times gravity times change in height. But what in the world is delta Z? Well, we'll come back to it in a second. First off, let's figure out the mass. So I have 50 people. There's 75 kilograms per person, which gives me a total mass of 3,750 kilograms. I know what gravity is. Gravity is 9.81 meters per second squared. But now I've got to figure out that delta Z. Now, there's various ways you can do this. I'm going to show you this one, and I'll show you another one at the end. So we just need to know how tall the escalator is, right? We can figure out how far it went, and we're good. But it doesn't actually tell us how tall the escalator is. We're stuck. We don't know anything. I'm kidding. The only way you can solve this one, well, there's multiple ways, but this is the best way, is to realize it asked for power. It didn't ask for energy, it asked for power. And so that means my change potential energy over time. And since I've got change potential energy over time, well, that means I've got delta Z over delta T, which is effectively equal to my velocity in the up direction. Okay, so that's not too bad. Now, we have a velocity here, but if I were to draw this, that's the velocity going up at an angle of 45 degrees, which, if you remember your trig, it's not too hard to figure out how to get that. So this right here is VZ, and so VZ will be equal to 1.05 sine of 45. Nice. And because I've got terrible handwriting, I typed all of that in. I forgot to type it in, but I just showed you how to get it. So this right here, that's 1.05 sine of 45 degrees. And if I plug all that, I have that my power to do this is 27.13 kilowatts in order to get everybody moving up the escalator. So it takes a decent amount of power because there's a lot of mass and a decent velocity. Another cool little detail here, which I don't mention, is there's a nice little equation which is power is equal to force times velocity. I'm putting a little arrow over that to make sure that you know that's velocity, not volume or something else. Force times velocity. So if I know the force I'm applying and I take the velocity in that particular direction, I can figure out the power it takes to do that, to maintain that motion using that force. Oh, and there it is. I have my animation in the wrong place. But that's where we got the vertical component of the velocity. Okay, I think that is most of this problem. So all we have to do now is figure out what happens if we double the velocity. Well, if I double the velocity, this guy's just times 2, which means this guy's times 2. So it doubles, and that's it. So thanks for watching, and I'll see you next time as we continue through Chapter 2. Bye-bye.